Welcome to the chapter on geotechnical engineering. This field is a crucial branch of civil engineering that deals with the behavior of earth materials. Understanding soil mechanics, earth retaining structures, and foundation design is essential for creating safe and effective structures. In this chapter, we will cover the fundamentals of soil mechanics, earth retaining structures, and foundation design. Soil mechanics involves the study of the physical properties and utilization of soils, especially in civil engineering. It focuses on understanding the behavior of soil under various conditions of stress and strain. Key properties of soil include density, which is the mass of soil per unit volume, usually expressed in kilograms per cubic meter. Porosity is the ratio of the volume of voids to the total volume of the soil. Permeability refers to the soil's ability to transmit water or other fluids. Shear strength is the soil's resistance to shear stress. Soils are classified based on their particle size. Gravel consists of particles larger than 2 millimeters. Sand particles range from 0.075 millimeters to 2 millimeters. Silt particles are between 0.002 millimeters and 0.075 millimeters. Clay particles are smaller than 0.02 millimeters. The effective stress principle is fundamental in soil mechanics. It states that the strength and deformation of soil are controlled by the effective stress, which is the difference between the total stress and the pore water pressure. The formula is sigma prime equals sigma minus u, where sigma prime is the effective stress, sigma is the total stress, and u is the pore water pressure. Consider a soil sample with a total stress of 100 kilopascals and a pore water pressure of 30 kilopascals. The effective stress can be calculated as sigma prime equals 100 kilopascals minus 30 kilopascals, which equals 70 kilopascals. Earth-retaining structures are used to retain soil at different levels on either side of the structure. They are essential in preventing soil erosion and managing slopes. There are various types of retaining walls. Gravity walls rely on their weight to retain soil. Cantilever walls use a reinforced concrete stem and base to resist pressure. Sheet pile walls are made of steel, vinyl, or wood planks driven into the ground. The pressure exerted by the soil on a retaining wall is known as lateral earth pressure. It can be calculated using Rankine's theory for active and passive earth pressures. Active earth pressure can be calculated using the formula sigma A equals Ka gamma H, where sigma A is the active earth pressure, Ka is the active earth pressure coefficient, gamma is the unit weight of the soil, and H is the height of the retaining wall. Passive earth pressure can be calculated using the formula sigma P equals Kp gamma H, where sigma P is the passive earth pressure and Kp is the passive earth pressure coefficient. For a retaining wall with a height of 5 meters, unit weight of soil 18 kilonewtons per cubic meter, and an active earth pressure coefficient of 0.3, the active earth pressure at the base of the wall is calculated as sigma A equals 0.3 times 18 kilonewtons per cubic meter times 5 meters, which equals 27 kilopascals. Foundations are structural elements that transfer loads from buildings or other structures to the ground. Proper foundation design is crucial for the stability and safety of structures. There are two main types of foundations. Shallow foundations, such as spread footings and mat foundations, are used when soil near the surface has sufficient bearing capacity. Deep foundations, such as piles and drilled shafts, are used when the surface soil is weak and loads need to be transferred to deeper, more stable soil layers. The bearing capacity of soil is the maximum load per unit area that the soil can support without failure. It can be calculated using Terzaghis bearing capacity equation for shallow foundations. Terzaghis bearing capacity equation is given by Q equals CNC plus gamma d FNQ plus 0.5 gamma BN gamma, where QU is the ultimate bearing capacity, C is the cohesion of the soil, gamma is the unit weight of the soil, dF is the depth of the foundation, B is the width of the foundation, and NC, NQ, and N gamma are bearing capacity factors. For a shallow foundation with cohesion of 25 kilopascals, unit weight of soil 18 kilonewtons per cubic meter, depth of foundation 1.5 meters, width of foundation 2 meters, and bearing capacity factors NC equals 30, NQ equals 18, and N gamma equals 15. The ultimate bearing capacity is calculated as QU equals 25 kilopascals times 30 plus 18 kilonewtons per cubic meter times 1.5 meters times 18 plus 0.5 times 18 kilonewtons per cubic meter times 2 meters times 15, which equals 1,506 kilopascals. Understanding these fundamental concepts in geotechnical engineering will help you design safe and effective civil engineering projects.